Every time you chat with a large language model, a silent computational storm rages inside the GPU. In autoregressive decoding, the model generates text one word at a time. But here is the catch. To generate the next token, the model needs to attend to every single token that came before it. If we recalculated all self-attention matrices from scratch at every step, the processing latency would scale quadratically, grinding generation to a painful halt. To solve this, modern engines use the key value, or KV, cache to store historical context. Today, we will demystify the mechanics of KV cache optimization, exploring how MQA, GQA, and PagedAttention conquered the memory wall. While the KV cache prevents redundant computations, it introduces a brutal physical bottleneck: memory capacity. The size of the KV cache is not trivial. It scales linearly with the batch size, sequence length, model depth, and the number of attention heads. Mathematically, the memory footprint in bytes equals 2 times the batch size, times the sequence length, times the number of layers, times the number of heads, times the head dimension, times the bytes per parameter. For a Llama 2 70 billion parameter model, running a batch of 128 sequences at a context window of 4,000 tokens. This cache alone consumes over 120 gigabytes of high-bandwidth memory. This causes GPUs to run out of memory, or OM, limiting throughput and concurrency. To alleviate this memory pressure, researchers looked at attention head architecture. Standard multi-head attention, or MHA, assigns a unique key and value head to every query head. To compress this, multi-query attention, or MQA, uses a single key and value head shared across all query heads. While this reduces the cache size by up to 8 times, it can degrade model accuracy because of the drastic loss in capacity. The elegant middle ground is group query attention, or GQA. GQA partitions query heads into groups, with each group sharing a single key and value head. For instance, an 8-to-1 ratio allows GQA to achieve almost the same speed and memory savings as MQA, while fully maintaining the high quality and accuracy of multi-head attention. But even with head compression, we face another massive inefficiency: how memory is allocated. Standard engines pre-allocate contiguous memory blocks for the maximum possible sequence length. Since most requests finish early, this results in up to 60% of the pre-allocated memory being wasted, a classic case of internal fragmentation. To solve this, PagedAttention adapts virtual memory techniques from operating systems. It divides the KV cache of each sequence into small, fixed-size physical blocks. Instead of contiguous allocation, physical blocks are mapped dynamically using a logical-to-physical block table. This allows non-contiguous storage, eliminates internal fragmentation, and enables different sequences to safely share key and value blocks, multiplying concurrency by up to 4 times. By co-designing attention head architectures and operating system-style memory managers, GQA and PagedAttention have redefined the efficiency frontier of deep learning. They allow us to run larger models, handle massive context windows, and serve thousands of concurrent users without changing the model's underlying weights. If you want to keep mastering the engineering breakthroughs shaping modern artificial intelligence, hit the subscribe button for Gemini 3.5 Flash model. Let's push the boundaries of performance, one physical block at a time.